So good morning, class, and welcome to today's lecture. Please, I have posted the YouTube link. So please help to share to those that won't be able to join us, because very soon we're already 300. So please, nobody, I don't think any other person can join. So please help to share the YouTube link so that everybody can participate in this lecture. And please put your details on the chat. That will serve as an attendance. And if you can hear me, please put it up on the chat. Let me be sure that I'm not speaking to myself alone. If you can hear me, let me put it up on the chat. Okay, thank you very much. Thank you and thank you. So we're already 300, so I think we can start. Others can now join via YouTube. So let me share my slide. Please, those that can't join, they should please join via YouTube. Okay. So this should be our third lecture. I remember the last lecture we stopped at radioactivity, where we looked at the radioactive particles and their nature, how you can, the instrument that you can use, the units. We looked at some calculations, nuclear reactions, and we ended with applications of radioactivity. So today we are going into something different, something new, which is stoichiometry, chemical equations, chemical reactions, and limiting reagents. So we are going to see some calculations today, because as you study chemistry, you must know chemical equations, how to write equations, how to carry out calculations from equations. So that is actually what we are going to be looking at today. So at the end of this lecture today, what do I expect from you? You should be able to carry out stoichiometric calculations, be able to balance chemical equations, and calculate limiting reagents. But for today, we are only going to look at stoichiometric calculations. The next lecture, which by God's grace is going to be our last lecture, then we'll be able to look at balancing chemical equations and limiting reagents. So today, we are going to start with stoichiometry. When we talk about stoichiometry, what are we talking about? We are just talking about chemical reactions, because in chemical reactions, we have the reactants and we have the products. So what happens in chemical reaction? The substances or the materials are consumed, which is the reactant. And when they are consumed, then you can be able to get the products. What do I mean? In a chemical reaction, you have A plus B giving you C plus D. So we said that in chemical reaction, you are looking at the reactants. These are the reactants. These are the reactants. and these are the products. So invariably, these ones are consumed for these ones to be produced. So that is what we are trying to explain in stoichiometry. So stoichiometry, this deals with the quantities of materials or substances consumed, which is reactant. I've already shown you using that equation, and materials produced, which are the product in a chemical reaction. So for us to be able to understand this concept, there are some concepts we need to look at. We have to look at some concepts, and some of those concepts are what we call relative atomic mass. We are going to see what is relative atomic mass and how it came about. We also look at their Avogadro's number. Of course, from your secondary school, we already know Avogadro's number. Most of the calculations, especially that has to do with mole, you have to apply your Avogadro's number. We also look at the mole concept, and we look at the molar mass. And from there, we look at the percentage composition of every compound. Now, the first we are going to look at is the relative atomic mass. When we talk about relative atomic mass, that means we are comparing something that when you say is relative to something. So relative atomic mass is the weighted average of the masses of an element's isotopes compared, that is that word relative, compared to the mass of a carbon-12 atom. And your relative atomic mass is dimensionless. That is a dimensionless quantity. That means it has no unit. Why do we say it's relative? That is compared to the mass of carbon, because atoms are very small. And so it is impossible to weigh a single atom. So because we cannot weigh a single atom, so what happens is that the mass of an atom can only be determined relative to another one experimentally. And most times the standard used in measuring these atomic masses of other elements is your carbon-12. So your carbon-12, which is the standard, is assigned a mass of exactly 12 atomic mass units. And this is not used as a standard in measuring the atomic masses of other elements. So for your carbon, of course, we are still going to see the atomic mass of your carbon. So for your carbon, we have carbon-12, we have carbon-13, we have carbon-14. Carbon-12 is the most abundant, about 98%. Then we also have carbon-13, which is about 1.1%. We also have carbon-14, but your carbon-14 is radioactive. So most times your carbon-14 is mostly used as in dating. That is to be able to know how many years a particular maybe substance have stayed on the earth. So it's used in dating. So the most abundant is your carbon-12, and we also have your carbon-13. So you see that most times, as we go on, you see what I mean by we only use your carbon-12 and your carbon-13. So looking at mass, because we are looking at relative atomic mass, so we are actually looking at the mass of the element. We normally use what we call the mass spectrometer to be able to get the mass, because as I already told you, these atoms are very, very small. So if you want to instrumentally, if you want to determine the mass of an element, you use what we call the mass spectrometer. But I'm not going to go into details into this. We don't need that. Just know the instrument that we use for us to be able to determine the mass of an element. So it's called the mass spectrometer. So having known what our relative atomic mass is, now, what do we mean by what is the average atomic mass? Because the relative we are comparing to carbon. Now, what is the average atomic mass? So don't mix both of them together. Average atomic mass, most times we refer to it as the atomic weight. It's not the mass of a single atom, because we are looking at the word there is average. So it's not the mass of a single atom, but rather the average masses of all the isotopes of an element. So for you to be able to get the average atomic mass, you must be able to know the mass of all the isotopes of an element. For example, if you look at our carbon-12, the average atomic mass of our carbon-12 is 12.01, not 12. So I ask the question, have you ever wondered why the atomic mass of carbon is 12.01 instead of 12? So don't make that mistake when you're looking at average atomic mass. You always try to get the average of the two isotopes. Most elements have isotopes, like your chlorine. We have chlorine 35, we have chlorine 37. So for you to be able to get the mass of your chlorine, then you need the average atomic mass. So that was why I asked the question, have you ever wondered why the atomic mass of a carbon is 12.01 instead of 12? So in an exam, if the option there is 12.01, 12.00, and you pick 12.00, then you know that it's wrong. This 0.1 is very, very important, especially when you are looking at the average atomic mass. And as I said, you have this because of the different isotopes. What do you mean by isotopes? That is two atoms having the same atomic number but different mass numbers. So invariably, we can calculate the atomic mass of every element. So let's look at one example. The common one is your carbon. As I said, we have carbon-12 and we have carbon-13. Your carbon-12 has a relative abundance of 98.89. So you know that this is the more abundance. That is the one we are used to. That is the one most of us know. But we also have our carbon-13, which only has a relative abundance of 1.11. So if you add these two together, you see that we have 100%. So that was why I told you that our carbon-14 is radioactive. You know why? Because it's radioactive, so we don't normally see it in free nature. So that is why for you to get the 100% of your carbon is when you add up your carbon-12 and your carbon-13. Now, for us to be able to get the average atomic mass, this is how, so let's look at the calculation. I know you already have it there, but let's. So for our carbon-12, the relative abundance is, we have to say it's 98.89 over 100 times 12 over 1. So this is for your carbon-12. While for your carbon-13, the relative abundance is 1.11 times 13. 0.00 over 100. So that is actually how to calculate. So when you are done with the calculation, then that will give us. So I think you can do that simple calculation. So that is how we are going to get 12.01 instead of 12. So 9.89 times 12 over 100 plus 1.11 times 13 over 100. So this is actually the average atomic mass of your carbon. So let's look at another example using chlorine. Your chlorine has two isotopes, chlorine 35 and your chlorine 37. Chlorine 35 has abundance of 75.53%, while chlorine 37 has 24.47%. So which one is more abundant? Put it in the chat. Which one among your chlorine 35 and 37, which one is more abundant? Put it up on the chat. Chlorine 35, thank you very much. So your chlorine 35 is more abundant and the atomic mass unit for each of them is given. So we said that it said calculate the average atomic mass of your chlorine. So how do we do that? I have it in the next slide, but let's look at the calculation. So it's just similar to what I've already calculated. For those of you that have your notebook, I expect you to have your notebook here. So can you do the calculation and give me the answer? So from what we have, we should have 75.53 times 34.968 over 100 plus 24.47 times 36.956 over 100. I'm sure you should be able to do that calculation. So what is the answer? Let me go to the chat. 35 point, it's 35.45. Don't abbreviate. So let's go back to our slide. So that is the calculation we just did. So the answer is 35.45. Please don't abbreviate, just leave it the way it is because it's the average. Is the average. So that is that for relative atomic mass and your average atomic mass. So we cannot carry out calculations, especially when we are looking at mole, without knowing what Avogadro's number is, because we really need the Avogadro's number to be able to get the actual number of moles. So what is your Avogadro's number? So your Avogadro's number is defined as 6.022 times 10 raised to the power 23 particles. These particles, they can be the atom, they can be the molecules, they can be the ions that is present in 1 mole of a substance. So for you to be able to know, carry out calculations, especially that has to do with mole, and most times the calculations we are going to carry out, you must know the number of mole. Like 1 mole of sodium is how many? If you want to calculate, if you are asked 1 mole of sodium, what is 1 mole of sodium? Because we said the Avogadro's number is defined as 6.022 times 23 particles present in 1 mole of a substance. So do I have answer in my chat? She has already done the calculation. Okay, don't worry. So let's not jump the queue. Let's just go one by one. So for Avogadro's number, it is a fundamental constant in chemistry. Your Avogadro's number is a fundamental. Thank you, Dave. You've already done the calculation. Don't worry. Let's go step by step. So thank you, those of you that gave the answer in the chat. But let me go step by step. So for your Avogadro's number, it is a fundamental constant. So it's a constant in chemistry. So because we normally use it when we are doing a relationship with the mole. So now, what is a mole? We've known what our Avogadro's number is. A mole is the amount of substance that contains as many atoms, molecules, or other particles as there are in exactly 12 grams of your carbon-12 isotope. And we say that because samples contain so many atoms, so the unit of measurement, the mole, has been used in counting the atoms. So most times, as I said, you always, once you know the gram, then you can be able to get the mole using your Avogadro's number. So in other words, it is the number equal to the number of carbon atoms in exactly 12 grams of your carbon-13. So 12 grams of your carbon-12 contains 6.023 times 10 raised to the power 23 atoms, because your Avogadro's number is a constant. So once you know the gram, you will be able to get the number of moles. So let's look at, so 1 mole of your carbon 12 is, of course, is your 0.23 times 10 raised to the power 23 atoms. For 1 mole of your water molecule, 6.02 times 23 water molecules. 1 mole of NO3 ions, 6.02 times 10 raised to the power 23 NO2 ions. So it has to be that particular, if it's the atom, the molecule, the ion, the particle. 1 mole of hydrogen atoms is 6.023 times 23 atoms, because we are looking at 1 mole of hydrogen atom. 1 mole of oxygen atom, 1 mole of hydrogen molecule. So that is 0.23 times 10 raised to the power 23 molecules. So you must be able to equate it to the number of mole of the atom, the ion, the molecule. So it's very, very important for you to be able to know how to equate this. So you cannot say 1 mole of hydrogen atoms contains 6.023 times 10 raised to the power 23 ions. Do you understand what I mean? It must contain, either is the molecule or is the atom or is the ion. That is why we say 1 mole of NO3 ion contains 6.023 times 10 raised to the power 23 NO3 ions. Please note that. It's very, very important. Okay. So now we say, let's use the example so that you can understand it better. We say calculate the number of hydrogen atoms in 0.35 mole of air. This is your glucose. So from this, we know that 1 mole of your glucose will contain how many? 12 moles of your hydrogen atom, because in this compound, your hydrogen here is actually, the hydrogen atoms is actually how many moles? 12 moles. So 1 mole of, so let me go to calculation. So we are looking at C6H12O6. And we are given that the number of moles of your hydrogen in this compound is 0.350. So what it means is that if 1 mole of your C6H12O6, of course, it will contain 12 moles of hydrogen atoms. It will contain, but now we are given how many moles? 0.35 moles. So therefore, 0.35 moles of this C6H12O6 will contain what? 0.350 times 12 over 1. And that will give us what? If you do that calculation, it's going to give us 4.2 moles of hydrogen atoms. So we are getting 4.2 moles of hydrogen atom. And we know that 1 mole of, that's why I say you always need your Avogadro's number. And we know that 1 mole of your hydrogen atom is equal to what? 1 mole of your hydrogen atom is equal to what? 0.023 times 10 raised to the power 23. Therefore, 4.2 moles that we already got will give us what? So can you do that calculation? So say calculate the number of hydrogen atoms in 0.35 mole of this. So I think, so we say that 1 mole of this contains 12 moles of hydrogen, which I've already, that is what I just explained. So 0.35 moles will contain 4.2 moles of hydrogen atom. But we know that 1 mole contains 6.02 times 10 raised to the power 23. Therefore, 4.2 will give us 2.54 times 10 raised to the power 24. So this is actually, so that is why you must know the Avogadro's number, especially when you are calculating the number of mole, because 1 mole of your molecule, 1 mole of your ion, 1 mole of your atom is equal to 6.02 times 10 raised to the power 23 atoms. So once you know the number of mole, then you can be able to know, you can now use your Avogadro's number. Once you know the number of mole, then you can now equate it to 1 mole of your atom or molecule using the Avogadro's number. So I have a class work here. Find both the number of moles of atoms and the number of atoms in 2.5 grams of sodium. And we know that 1 mole of sodium is equal to 23 grams. 1 mole of sodium is equal to 23 grams. Can we do that calculation? Okay, I'll do the first one, then we can now do the second one. So find both the number of moles. So getting the number of moles here is very easy. We know that 1 mole of sodium is equal to 23 grams. Okay, it's the same thing as 23 grams is equal to 1 mole of sodium. And we have 2.5 grams of sodium, so we can be able to get that. So let me go to the calculation. Let it not look as if I'm speaking Greek. But it's a simple calculation. I know some people are already putting the answer in the chat. That's good. You people are impressing me. So from the question, they said that 1 mole of sodium is equal to 23 grams. It's the same thing as saying that 23 grams is equal to 1 mole of sodium. And from the question we are given, we are looking for 2.5 grams. So if 23 grams is equal to 1 mole of sodium, then 2.5 grams will give us what? 2.5 times 1 over 23. If you do that calculation, this should be able to give us 0.11 moles. And again, we know that 1 mole contains 6.02 times 10 raised to the power 23. Therefore, 0.11 mole will contain, that is a simple calculation. So let me go to the charts. Do we have answers in the chat? Thank you very much. Okay. Okay. So I already have it, but I just wanted to do the calculations there. So 23 grams is equal to 1 mole of sodium. Therefore, 2.5 will give us 0.11 mole. And we know that 1 mole contains 6 point this. So 0.1 will contain this 6.6 times 10 raised to the power 22 atoms. Because that question says calculate the number of moles of atom and the number of atoms. So this is the number of moles and this is the number of atoms. So the second question says a sample of cobalt contains 5.0 times 10 raised to the power 20 atoms. Calculate the number of moles to the mass of the sample. So I will leave that as an assignment for you so that we can continue, so that we can finish up what we have now. So we've looked at the relative atomic mass. We have seen how to calculate that. We've also looked at the Avogadro's number. We've also looked at the mole, how we relate the number of mole to the Avogadro's number. Now, the next we are going to look at is the molar mass. What do we mean by molar mass? Molar mass of a substance is the mass in grams of 1 mole of a compound. And how do you get the molar mass? I'm sure you did this in secondary school. By summing up the atomic masses of all the component atoms in a particular compound or substance. So if I have your sodium hydroxide, if I ask you what is the molar mass, it's just summing up the mass of your sodium and your oxygen and your hydrogen. That will give you the what? The molar mass. So we will say that it is the mass in gram of 1 mole of a compound, and you can get this by summing the atomic masses of all the component atoms in a particular compound or substance. For example, 1 mole of magnesium atom is 24.31 gram. Therefore, the molar mass is 20. Listen very well. It's like, say, if I can say, of course, like 1 mole of your sodium is 23 gram. That is the same thing as saying 1 mole of your magnesium atom is 24.31 gram. But the molar mass, that word molar, so the unit is going to change. The mass is the same, but because we are not looking at molar, so the molar mass of your magnesium atom is now going to be 24.31 gram per mole. Just like the molar mass of your sodium is going to be 23 gram per mole. So please, when you are, mass is different from molar mass. Mass is in gram. Molar mass is in gram per mole because of that word molar. So the molar mass of your methane is what? Let's do the calculation. So we are looking for the molar mass of your CH. Do I even need to do that? Can you do that in and put and help and give me the answer in the chat? That is very simple now. Isn't it? That's a very simple question. The molar mass of your CH for your methane. Molar mass of your CH4. That is your 12. Carbon is your 12. Of course, it's 1. Plus hydrogen is 4. 1 times 4. So what is the molar mass of your methane? Let me go to the chart. 16 gram per mole. Thank you very much. 16 gram per mole. Thank you. So 16.04 gram per mole. You see, because of course, you see why you have 0.4? Because of what? Your carbon, this is the average atomic, the relative atomic mass or the average atomic mass. You, of course, we do look at that where we got it as 12.01, and also your hydrogen. Of course, your hydrogen we have your hydrogen as 1.008. So that is why you are, instead of 16, you're getting as 16.04 gram per mole. I was just trying to stress that because it's smaller, then you have to add the gram per mole. So please try and get the exact mass of most of the elements, especially those that have isotopes, so that we can be able to get the average atomic mass. So having known how to calculate the molar mass, which is very, very important for you to carry out a lot of calculations, let's now see the relationship between the mass, the number of moles, and your molar mass. Especially in your titrations, I'm sure you are going to come across this very often. This formula is very, very common in your titration, where number of moles is equals to mass over molar mass. So this is the relationship between mass, molar mass, and number of moles. So most times, you are not given the number of moles, you'll be able to, if you are given the mass, you should be able to get the molar mass. If you are given the mass is what you weighed, and you know the molar mass from your calculation, then you can be able to calculate the number of moles. So it's this formula should be at your beck and corner. Let it be at your fingertip, because you will need it for a lot of calculations. Now, having known how to calculate molar mass and the relationship between the mass, number of moles, and molar mass, let's now look at percentage composition of elements. So this is where we are actually going to put these formulas into action or into use. So to determine the percentage composition of element in a compound, you have to determine the molar mass of the compound before you can determine the mass ratios. So you have to know how to calculate the molar mass. So let's look at some example. I always like using examples so that you can understand what we are talking about. So for the percentage composition, of course, first of all, we have to get the molar mass. So we are looking at what is the percentage composition of potassium permanganate. So the percentage composition, so we want to know the percentage composition of your potassium permanganate. So in this compound, what is the percentage of potassium? What is the percentage of manganese? What is the percentage of oxygen that make up this particular compound? So for your potassium, of course, we say we have to know the molar mass. From the molar mass, then we can be able to know the percentage composition. And you are going to do that for me. So for your potassium, it's a 39.1. Of course, it's only 1 times 1. Your manganese is what? 54.9. It's only one of it times 1. And your oxygen, of course, your oxygen is 4. So it's going to be 16 times 4. And that will give us what? This will give us 39.1. This will give us the same 54.9. And this will give us 64. And when you add that, that will give us what? 158 gram per mole. So that will give us 154. That is, first of all, we have to calculate the molar mass. Now, after calculating the molar mass, you are now going to give me the percentage composition for each of them. Can we do that and put it up in the chart? I have it here, but I want you to do that. So can I have the percentage composition for each of them? We already know the molar mass. I can't see anything in the chat. Okay. So for potassium, it's going to be 39.1 over the molar mass times 100. It's just a simple calculation. I wanted you to do that. For manganese, 54.9 over the molar mass times 100, and oxygen, 64 over 158 times 100, because we are looking for the percentage composition. What is the percentage composition of your potassium, your manganese, and your oxygen? Of course, it's going to be the mass over the molar mass times 100 over 1. Okay, I can see that in the chat. Thank you. Thank you. It's only David that answered. Only David. Okay, Emmanuel, thank you. Thank you. So the most important thing is that we know how to calculate the molar mass, which I've taught you, and also to calculate the percentage composition. So after getting the molar mass, you can then look for the percentage composition for each of them. Okay, calculate the percentage composition of each of the atoms present in your phosphorus acid. Calculate the percentage composition of each of the atoms present in your phosphorus acid. Of course, the first thing we are going to do is to calculate the molar mass. Your hydrogen is 3 times 1. Your phosphorus is 30 times 1, which gives us the same 30. And your oxygen is 16 times 4. So the molar mass is 97.99 gram per mole. So now, how do we calculate the percentage composition for each. Can you do that and put it up in the chat? So what is the percentage composition for your hydrogen, your phosphorus, and the oxygen? People are still calculating the last one. What? I want you to give me this answer. I'm waiting. So for hydrogen is going to be 3 times 1.008 over what? 97.99 times 100 over 1. This is 30.97 over 97.99 times 100 over 1. And this is 4 times 16 over 100 over 97.99 times 100 over 1. And that is it. So let me go back to the chat and see those that have been able to answer. Okay. Thank you very much. Most of you got it correct. So this is how you calculate it. It's a simple calculation. First of all, you calculate the molar mass. Once you get the molar mass, then you'll be able to get the percentage composition for each of the elements. And again, the percentage composition must add up to 100% because that compound is complete. So if you do your calculation and you don't get 100%, then you will know that there's something wrong somewhere. You know that there's something wrong somewhere. So the next is, of course, we are saying this is a class work. Determine the percentage composition of ethanol. What is this percentage composition of ethanol? So let's just do that. I think you can do that very comfortably. I'm very, very confident that you can do that calculation. So you should expect most of the calculation. Percentage composition of your C2H5OH. First of all, we calculate the molar mass. Your carbon is what? 12. That's 12.01. Am I correct? Times 2 plus hydrogen is 1 times 5 plus oxygen is what? 16 times 1 plus another hydrogen is what? 1 times 1. So this will give us what? If you add this sum, the sum total is going to give us what? So this is 24. 24.02, if I'm correct, plus what? 5, plus what? 16, plus 1. And what is that total? What will that give us? That will give us what? Maybe like, is it 46? Am I correct? 46 point something. So that is the molar mass. So if you're not looking for carbon, your carbon is going to be what? How many? That is not going to be, of course, 24.02. 0.02 over 46 times 100 over 1. So you can do that for each of them. So I'm waiting. Can you do that calculation and let me have the answer in the chat? Those of you via YouTube, can you hear me? Please do the calculation, everybody, and put it up in the chat. 54.1, okay, carbon, hydrogen, oxygen. Thank you. Thank you. Those of you via YouTube, can you hear me? Are you following? Those of you via YouTube, can you hear me? Are you following? Okay, thank you. Thank you very much. I can see those of you in via YouTube you are responding to. Thank you. I can see your names, your responses. Thank you, thank you, thank you very much. Thank you. Okay. Okay. So let's see. What do we have? What is our answers? Carbon 52.13%, hydrogen 13.15%, and oxygen 34.72%. Most of you got it correctly. Now, determine the percentage composition of sodium oxalates. Sodium oxalates. We are going to do this. So please, I already have the answer. So please, I want you to lay your hands on this and try to do the calculation. It's also very, very easy. I think the most important is for us to calculate the molar mass. Once we know the molar mass, then the percentage composition is not difficult. You know, there are simple calculations that, so sodium oxalates. So we have our sodium 23 times 2 plus 12.01 times 2 plus 16 times 4. That will give us the molar mass in gram per mole. And with that, we can be able to calculate the percentage composition. Okay, so with that, you'll be able to calculate the percentage composition for your sodium, your carbon, and the oxygen. So please, any question? Thank you, thank you, thank you. So any question? Question? Your test will be, I think when we are all done, I'm the third lecturer, so I intend to finish either by Monday. Whatever is left will finish on Friday. I should be done next week with my lectures. So the next lecturer will come in. So I want to presume it's when, I think we are about 6 lecturers. I'm the third person. The fourth person is coming in. So we still have after me, we still have like 3 more lecturers. So the next person will come after me, then we have like 2 more. So I'm sure it's when we are all done that we can have the test, because you cannot just have tests for just the 3 lectures you have done. But I'll confirm from the coordinator of the course. I'll confirm from the coordinator of the course. So any question? Any question? Any question? Okay, that means it's well understood. Thank you very much. So our next lecture will be on Monday. That should be the last. That should be the 4th lecture, where we look at we're gonna look at the chemical equations, balancing chemical equations, limiting reagent, and percentage yield. So it's also interesting. It's not something difficult that we are going to just, most of you already know how to balance your equation. We still look at using the number of moles, and it's not something difficult. It's something we can easily do, and you calculate. That's it. Classwork, limiting reagent, and percentage yield. So we'll meet on Monday, God's willing. If we can finish on Monday, fine. If we cannot, then we'll complete it on Friday. Whatever is left, we'll be able to complete that on Friday. How is the test going to be? It's going to be like your exam. I think it's going to be CBT, MCQ. So I think so. I want to presume so. I don't know if it's going to be Zoom test or if you're going to come to class. That I don't know. It's the coordinator that will decide on that. But for now, attend your lectures and read your books. So I'll see you on Monday, God's willing. You say, is there going to be a makeup lab? Which lab? I don't know. I'm not in lab 106. I'm not in the year 1 lab, so I don't know if there's going to be a makeup lab. Yes, I will send you my slides. Once I'm done, I'll send the slides, lecture by lecture. I already have them fashioned out lecture, but the way I taught it, the way I send it via recording. So I'll send you the slide, but attend your lectures first. Thank you so much. So I'll see you on Monday, God's willing. Bye.